Hi, this is Yashwant, and I'm going to be presenting our work on algorithms for heavy tail statistics. The joint work with Sam Hopkins, Tarun Katuria, Prasad Raghavendra, and Nilesh Tripuraneni from UC Berkeley. And we're going to be focused on the problem of high probability estimation. And we're going to be focusing on the problems of covariance estimation and linear regression. So for covariance estimation, you're given access to n IID random vectors, x1 through xn, with covariance matrix sigma. And you want to design an estimator sigma hat, which is within a radius r delta in spectral norm of the true covariance matrix sigma with probability at least 1 minus delta. So for linear regression, you have a similar setup. You're given access to n IID samples, yi, xi, where yi is the inner product of xi with w star plus some independent noise epsilon. And you want to design an estimator w hat, which is within r delta of w star in Euclidean norm with probability at least 1 minus delta. And in both of these setups, you want to focus on settings where delta is really small, say exponentially small in the dimension. And you want to make r delta really as small as possible as a function of delta n and the dimension d. So this problem has previously been explored for mean estimation. And for this particular setting, we know optimal statistical and computational results. So just to get an estimate of what we could shoot for, let's consider the simplest case where the data is generated from a Gaussian distribution. So let's say that xi is generated IID from a Gaussian distribution with mean 0 and covariance matrix sigma. And in this setting, you can show that the empirical covariance matrix sigma hat is within a radius of root trace sigma over n plus the spectral norm of sigma times root log 1 over delta over n of the true covariance matrix sigma with probability at least 1 minus delta. To make this rate a little more interpretable, we're going to set trace sigma, we're going to consider a setting where trace sigma is O of d, the spectral norm of sigma is O of 1, and delta is exponentially small in the dimension. And with the setting of parameters, like the rate simplifies to a rate of square root d over n, which we can show is statistically optimal. And so we're in this fortunate scenario where a polynomial time estimator gives you statistically optimal rates. So now let's consider a similar problem for linear regression. So xi are again from a Gaussian distribution with identity covariance, and the noise terms are IID are independent of xi, again from a Gaussian distribution with variance 1. And you can show that the OLS estimator, which you can compute in polynomial time, gives you a rate of root d over n plus root log 1 over delta over n. Again, when you set delta to be e to the negative d, this rate simplifies to O of root d over n, which again is statistically optimal. So here again, you have a polynomial time estimator, which gives you statistically optimal rates. So now what happens when you relax this assumption of Gaussianity? What kind of rates can you hope to expect? So again, we're going to focus on the setting where delta is e to the negative d. So in this setting, we know that the geometric median approach, or Minsker, gives you a rate of d over root n. The good thing about this approach is that it's computable in polynomial time, but it's statistically suboptimal. On the other hand, the approach based on the median of means tournament estimator by Mendelssohn and Zivotofsky gives you a rate of square root d log d over n. This is almost statistically optimal. It's only suboptimal by a factor of log d, but we don't know any efficient estimator to actually compute this estimator. We don't know of an efficient algorithm to actually compute this estimator. And now the question is whether you can break this d over root n barrier in polynomial time under these weak assumptions. So let's explore a similar problem for linear regression. So again, delta is e to the negative d. And in this setting, you can show that the geometric median approach of Su and Sabato gives you a rate of d over root n. But it only applies when n is much larger than d squared, and it's statistically suboptimal. But on the other hand, you can actually compute this in polynomial time. On the other hand, there is the median of means tournament estimator by Lugosi and Mendelssohn, which gives you a rate of root d over n, which is statistically optimal. And it kicks in as soon as n is larger than d, but then we don't know of an efficient estimator to actually compute this. So again, here the question is whether we can break this d over root n barrier in polynomial time. So we show that under certain settings, we can break both of the barriers that we spoke about previously. But our assumptions are a little bit more stringent. So specifically, we will place the assumption of certifiable hypercontractivity on the vectors x. So the assumption states that there exists a constant L such that L squared times the variance of x along the direction u raised to the power 4 minus the eighth moment of x along the direction u raised to the power, sorry, the eighth moment of x along the direction u. It's a sum of squares polynomial in u. So not only are we enforcing the assumption that it's certifiably hypercontractive, we also want this to be certified by a sum of squares polynomial. And this assumption has been central in much recent work in high-dimensional statistical problems like robust mean estimation and clustering. And it holds for a broad class of distributions. So it holds for product distributions with bounded eighth moments, any linear transformations of product distributions, and distributions with eighth moments match those of a strongly log concave distribution. So for the rest of this talk, we will refer to distributions over X which satisfy this assumption as nice distributions. And our main theorem for covariance estimation is that we can get a rate of d to the 3/4 over root n in the setting where delta is exponentially small in the dimension. But so this in fact breaks the d over root n barrier that we had previously for polynomial time estimator at the cost of slightly stronger assumptions. So we assume eighth moments instead of fourth moments. And on top of that, we also assume the certifiability of the hypercontractivity assumptions. For linear regression, we have similar results. We can give a confidence interval of square root d over n when delta is exponentially small in the dimension. But this rate only kicks in once n is greater than or equal to d to the 3/2, as opposed to when n is greater than d, which we had for the information theoretically optimal estimator. So again, here our nice assumptions are stronger than ones that existed previously. But we also get but there's also the first polynomial time estimator that gives you the optimal rate. So through the rest of the talk, we are going to look over the median of means framework for covariance estimation. We're going to briefly touch upon the certification to search paradigm for solving such problems. We're going to talk about the SOS relaxations of the previous problem and how this leads to efficient algorithms. And we'll finally give a heuristic lower bound through the lower degree likelihood ratio test. So let me first introduce the median of means framework. So the setup is really simple. You take all of your data, you partition it into k batches. You compute some local estimate of the parameter you're trying to estimate in each of the batches. So you get k different estimates, sigma hat 1 through sigma hat k, and you want to combine them in some particular way. You should really think of this parameter k as quantifying a trade-off between how confident you want to be and how accurate your prediction is. So once you increase k, you can have like a higher confidence prediction, but the accuracy of your prediction is going to go down. So your confidence interval is going to be larger. So roughly k is related to delta, as k is going to be of the order of log 1 over delta in all of these settings. So in our setting, k is going to be roughly d or O of t. So in the one-dimensional case, this is really simple. And this has been discovered several times in the past by Nemirovsky and Newton, Jerem, Vazirani, and Valiant, and Alon, Matthias, and Segedi. And here you simply set your combining function f to be the median of your estimates. And you can show that once you do this, you get a confidence interval of root log 1 over delta over n. So now let's move on to a slightly more intricate setup. So what happens once you go to higher dimensions? And we're going to explore the framework of the median of means tournament estimator. I won't describe the estimator itself, but simply describe like the geometric insight that underlies its success. So it succeeds if the following conditions hold. For all unit vectors v, the quadratic forms of your local estimate sigma hat I is close to the quadratic form of v for the true covariance matrix sigma for at least 0.9k of the I, for at least 0.9k local estimates with probability at least 1 minus delta. And it's close to within a factor of square root d over n plus root log 1 over delta over n, which is the rate of recovery that you can expect. So in pictures, what this is simply saying is that if you consider a slab of thickness r delta with normal vector VV transpose around the true covariance matrix sigma, at least 0.9k of the sigma hat I, denoted by these blue dots, lies in this slab. So if you have this particular property holding for the sigma hat I, you get the optimal rates. And you can show that this holds with probability at least 1 minus delta. So now let's move on to a slightly different problem. Let's say I give you a candidate matrix M, and I want to test if M is really far from sigma or not. So given a candidate matrix M, I either want to certify that M is far from sigma by showing a candidate V for which it disagrees with most of your local estimate sigma hat I, or you prove that no such V exists, which in fact shows that M is close to sigma. So yeah, so we're going to focus on this testing problem from now onwards. Now I'm going to formally write out this testing problem as this polynomial program. So this is a polynomial program in variables v and bi. The variable v denotes the direction, and bi satisfies this polynomial equality bi squared equals bi. So bi is either 0 or 1. So bi in fact acts as an indicator variable, and what it indicates is that sigma is that the ith local estimate sigma hat I disagrees with M along the direction V. And we're going to say that this test succeeds if the value of this program is greater than or equal to 0.9k by exhibiting a candidate direction V. And what one can show is that the smallest r such that this test fails for the true covariance matrix sigma is the rate that you can expect for the median of means tournament estimator. And Mendelssohn and Zivotofsky showed that this R is of the order of square root d over n, which is a statistically optimal rate. So now this is a non-convex optimization problem. To come with an efficient variant, we instead solve the degree 8 SOS relaxation of the problem. And from previous results, which use this testing to estimation framework, you can efficiently go from this testing problem to actually estimating the quantity that you're interested in. And the extent to which the accuracy to which you'd be able to estimate sigma is the smallest r such that this SOS relaxation of this test fails when instantiated with the true covariance matrix sigma. So now the main question that we would want to address is, how do we bound this value of r delta SOS? So what is the smallest r such that this test fails for the SOS relaxation of this testing problem? So now we're going to designate this variable z to be the value of the SOS relaxation when instantiated with sigma and r delta SOS. So now the analysis of this quantity really follows through two steps. The first thing that you would note is that z satisfies a bounded differences condition, so it concentrates around its expectation. The second thing that you would do is actually bound the expectation of z. So since you know that z concentrates, the only thing that you have to do is show that the expectation of z is small. So let's just briefly touch upon the concentration step. So recall that z is given by the SOS relaxation of this program. Changing a single sigma hat I can only change the value of z by at most 1, because the objective value is simply the summation of the bi's. And each bi only interacts with a single sigma hat I. So when you change a sigma hat I, you can at most change the value of this program by 1. And what this means is that z satisfies a bounded differences condition, and from the bounded differences inequality, you can show that z is close to its expectation with high probability. So you can show that it's close to expectation with probability at least e to the negative some constant times k. And since we set k to be of the order of log 1 over delta, so this is the probability with at least 1 minus delta. So now we need to bound the expectation of z. So we're going to just set up some notation. So we're going to let this set script s denote the set of pseudo expectations which satisfy these polynomial inequalities. And these are precisely the same set of polynomial inequalities that we use to define our program. So there are pseudo expectations over b and b, which satisfy norm b squared equal to 1, bi squared equal to bi, and the deviation inequalities in terms of b and b. Now, what we can show is that the value of z through a not so difficult computation is that the value of z is upper bounded by square root k times root of the SOS norm of the tensor products of the deviations of sigma hat i's from sigma minus the expected value of these tensor products. So the main quantity that we need to bound is the term inside the square root, which we're now going to designate as y. And as a first pass as to bounding the value of y, one thing that you could do is upper bound the value of y by the spectral norm of this tensor producted matrix, because this is an inequality that SOS can certify. And now you can apply the standard matrix Bernstein inequality to try and control this quantity. But the problem with trying to carry out this approach is that the value of y is going to be determined by the matrix variance of this random matrix. And you can show that this random matrix in this particular setting is of the order of d cubed, which is fairly large. But on the other hand, the SOS variance of the quantity that we're interested in is not very large. It's just d squared as opposed to d cubed, which is the value of the matrix variance. And so to leverage this assumption, we came up with this new SOS Bernstein inequality, whose deviation bounds depend on the SOS variance of the random matrix as opposed to the matrix variance. And this is essentially proved by taking like a clever preconditioning of the random matrix whose spectra you want to control. And the intuition is that it quashes directions where the SOS norm is small, but the matrix variance is large. So this inequality was anticipated in prior works where it was proved for the specific case where the data is generated from a Gaussian distribution. But we show that this inequality holds more generally if you just have certifiably hypercontractive assumptions instead. And by plugging this SOS Bernstein bound, the bound that we get on the expectation of z is that it's at most 0.5k when you set r to be d to the 3/4 over root n. And since we know that z concentrates around its expectation, this concludes the proof of the lemma and gives us our rate of d to the 3/4 over root n. We also give heuristic evidence of hardness for this covariance estimation problem. Recall that like an important algorithmic primitive that we use was that given access to d covariance matrices sigma 1 to sigma d, you want to find a unit vector x such that the quadratic form of x with sigma I is large for at least d over 4 of the matrices. And in our setting, we set these matrices sigma I to be the centered empirical covariances of n over d samples. And what we were able to show is that r is less than or equal to d to the 3/4 over root n up to log factors. At the granularity at which we deploy our results, we show that these techniques can also distinguish between the following two distributions over random vectors. So let's say you had n samples, y1 through yn, which come from like a standard Gaussian distribution with identity covariance. And then you have a planted distribution where you divide these n samples into k batches. In each batch, the covariance matrix of y is either slightly larger or slightly smaller than the identity in a random direction. And for this problem, which we can show our algorithm successfully distinguishes between these null and planted distributions, you cannot beat this rate of d to the 3/4 over root n with a low degree test, which our algorithm is a specific instantiation of. So in the low degree likelihood ratio framework, you cannot beat this. This offers heuristic evidence that you can't beat the rate of d to the 3/4 over. So that's the end of the talk. Thank you for listening.